Hi guys, and welcome to the next lesson, pre-lesson 5, which covers core charge, first ionization energy, and electronegativity. And these are key properties of the periodic table. So under Unit 1, Area of Study 1A, 12.4, in the VCEA study design, this is the information that you're required to know. In last lesson, we covered the periodic table as an organizational tool and identified patterns with the groups and the periods. Now, this lesson we're going to talk about the electronic configuration and atomic radii, and we're also going to talk about properties like electronegativity and first ionization energy in the periodic table and how this is organized. Next lesson will cover metallic character and non-metallic character and the reactivity of the metals in the periodic table and how this is organized. So today, all of the underlined points is what we are going to be covering. The core charge is a measure of the attractive force felt by the valence electrons to the nucleus of an atom. So what's a valence electron? Well, a valence electron is simply the electrons in the outermost energy or the outermost shell of an atom. So this one here, sodium, it has one valence electron because it has one electron in its outermost shell. This carbon atom has 4 electrons in its outermost shell, therefore it has 4 valence electrons. The core charge can be quantified or measured by the attraction of the electrons to the nucleus. And the formula to do that is the number of protons in the nucleus minus the number of total inner shell electrons. The number of total inner shell electrons is simply the number of all the electrons except the valence. So for sodium here, it has 11 electrons in total, and it has one valence electron. So we know that it's got one valence, its total number of inner electrons would be 10. So the inner shell electrons would be 10 for sodium. An example of this here, chlorine has 17 protons and electrons, it's a neutral atom, and 18 neutrons. So 17 protons and electrons and 18 neutrons. To identify its valence structure, you can use the periodic table and locate where it is, what period it is in the periodic table, or you can write it out like this. So we have 1s2, 2s2, 2p6, 2s2, 3p5, so 2, 4, 10, 12, 17. So that equals 17 electrons, which is correct. Now, it has 7 valence electrons. Again, you can determine this from the location in the periodic table, the group in the periodic table that it lies in. It's got 7 valence electrons. So it has 7 valence electrons, and it has a total of 17 electrons. It must have 17 minus 10 equals 7 inner shell. 10 inner shell. 17 is the total number of electrons it has. It has 7 valence electrons, which means it would have 10 inner shell electrons in total. So the core charge would be the number of protons, which is 17, and you minus the number of total inner shell electrons, which is 10. So its core charge would be written as 10. Second example, determine the core charge of aluminium. So to do this, or to work out the core charge of aluminium, first of all, we need to know the atomic number. Atomic number is 13, so it's a neutral atom, so it would have 13 electrons because it has 13 protons. Its electron configuration is this. It has 3 electrons in its outer shell here. We know that from the group that it's in the periodic table, and we know the period gives us the electron configuration. The core charge is simply 10 inner shell electrons, these here, 2, 4, 10, and then 13 is the total number, so it's 13 minus 10, which is plus 3. So its core charge is plus 3. First ionization energy. This refers to the amount of energy required to remove an electron from the outer shell of the electron. So how much energy is required to remove valence electrons, basically. So sodium atom has electron configuration of 281 in the Bohr model of the atom, and it would like to lose this electron because it's more stable. So the ionization energy is the energy required to remove that electron or to release that electron. This is the properties of the periodic table in terms of first ionization energy. So as you move down a group, so here's the periodic table. As you move down a group, the first ionization energy will be decreasing. The reason is it doesn't take as much energy to remove that outer shell electron because there's more electrons to remove and they have less attraction to the inner core of the nucleus. As you move left to right across a period, these elements they want to gain electrons more, so they're not going to be able to rip off the electrons as easily. So therefore, left to right across the periodic table, you're going to have an increase. So moving this way, you have an increase in the ionization energy. And definitions and explanations are here. Electronegativity. Now this explains core charge and works on core charge a little bit too. Electronegativity refers to the ability of an atom or electron to attract electrons towards itself. So the more strongly attracted the valence electrons are in that atom, the closer they are pulled to the nucleus and the greater the electronegativity. So for example, if we were to look at hydrogen fluoride, this is a highly electronegative atom, electronegative compound. We can see that these are the electrons drawn around the fluoride, and there's an electron in between them here as well on this little bond. If you look at a ball and stick model, the green shows the presence of an electron, where the electron is, and this is the hydrogen. So most of the electron is over here, most of the time. If you look at electrostatic map, so what that is it's showing you from positive to negative, and electrons are negative, remember? So electrons are negatively charged. So this map is like a heat map, showing you where the negative charge is in red and where the positive charge is in blue. So you can see that most of the charge, negative charge, is held over here in the fluoride. So that tells you that it's attracting more electrons. There's more electrons over here on this red side, which means that it's more electronegative. So as you move across a period, so from left to right across the periodic table, you can see that the electronegativity increases. Fluorine here, very high electronegativity. It wants to gain electrons or wants to pull them closer to itself. If you go back towards the left, you can clearly see that something like hydrogen or lithium or sodium have a low electronegativity. So they don't want to pull electrons. They don't have a very strong pull for electrons to their nucleus. They want to lose them. As you move down a group, the electronegativity also decreases. So you can see it started at 1 and we moved down to 0.7. This is because if you look at these atoms, they're much bigger. They have many electrons in their shells. So if they have more electrons, it's harder to pull or control. Pull electrons to nucleus. So that means they would have a low electronegativity as you move down the group. So they increase the number of electrons as you move down the group, meaning it's harder. You're holding on to more things. Imagine you're trying to protect all of your lollies from your friend, and you've got, say, 10 lollies, 11 lollies here, and sodium does. That's much easier to protect. Whereas if you have 50, 60 lollies, it's harder to protect, and they can easily pull them off. That's why electronegativity, or the ability to attract to the nucleus, is much lower for these atoms and elements compared to these ones here. So this is just showing you the trend of electronegativity, which I've already explained, as it moves across the periodic table. As you move from left to right, it increases electronegativity. As you move from the bottom up, it also increases. So if you move from the top down, it would decrease. The atomic radius, come to next, gets larger as you move down, and it will get larger as you move from right to left. And this just shows you how electronegativity changes. I already said decreases as you move down a group and increases as you move left to right. Atomic radius. So a radius, as we probably know from mathematics, radius refers to distance between these two objects here. That's the So here's a circle, and this is the diameter, the entire distance, and then half of that distance would be the radius. The radius is the size of the atoms. So if we look at here, the definition. The atomic radius is equal to the distance between the nucleus and the valence electrons in the outer shells. So here's your nucleus, here's your valence electron in the outermost shell. This distance here, from here to here, that will be your atomic radius. Now, as you move down a group in the periodic table, it will increase. The reason is you have more electrons, meaning it's going to take more energy to hold on to those electrons, so the atom will become larger in size. As you can see, more electrons, you have a larger amount of electrons to hold and contain. It's harder to pull them to the center of the nucleus, so it will become larger. As you move from left to right, it decreases. These atoms here, they want to gain or hold electrons. So they will pull them in very tight. The reason is they want to gain a full outer shell of electrons. They want to have 8 electrons in their outer shell. So 8 electrons in outer shell. And because of that, they will want to gain them, meaning their atomic radius will become smaller. So these are some trends here. You can look through this in your own time. You can see how atomic radius changes, melting point changes, electronegativity changes, ionization energy as well, how that changes, or the ability to remove an electron from the atomous shell. These are the summary for today. Core charge refers to the charge of an atom. And there's a formula to calculate that. Electronegativity refers to the attraction of the valence electrons in the nucleus. It increases as you move from left to right. The periodic table. Atomic radius refers to the size of the atom in terms of how big it is from the nucleus to the valence electron, and it decreases in size as you move from left to right across the periodic table. These are the questions I'd like you to complete. Questions 1 to 3 of Chapter Review 2.2, page 46 of Chemistry 1 textbook. Thanks.